last lecture we saw representation of numbers on a digital computer of both the floating point and the integers. Today we continue on that topic and discuss some of the implications of that. Before we do that, we just summarize what we did yesterday, or we recap on what we did yesterday. We talked about the range of integers on that can be stored, that can be represented on a digital computer. For example, we looked at the range of integers in the base 2 that can be represented on a 16-bit computer. So we said that on the 16 bits, the first bit holds the sign, and the remaining 15 bits can hold binary numbers from all 0 to all 1, right? So the upper limit is all 1, of course, right? So that can be converted to the integer as 1 into 2 to the power of 14, right? So there are 0 to 14 bits here. That's 15 bits, and 1 bit is for the sign. So that is 1 into 2 to the power of 14 on base 2 all the way to 1 into 2 to the power of 0. So that's equals to 32,767. And we saw that we would think that on a 16-bit computer that it is minus 32 to 32,767 to 32,767 is what we can store, because 1 bit is for the sign. But one thing is that even all the bits are 0, it's 0, we know that, okay. So there is no need to store that. So all zeros can be used to store one additional number, and the convention is that that is used to store one more negative number. So we have minus 32,768 stored in the machine. So the range goes from minus 32,768 to 32,767. Okay, so that's the idea. So we always have one more negative number than that. We saw that using a program yesterday, that we have one additional negative number than a positive number. So coming back to the floating point representations, we said that the floating point is represented on the following form, that is, we have m b to the power e. Right. So m is a mantissa and b is a base and e is the exponent. That's what we saw yesterday. Right. So the mantissa has a finite number of bits. Okay. Exponent has a finite number of bits, and the base is fixed. Okay. So that determines the range of floating point numbers which can be fixed, which can be represented. So we will see that in a more graphical representation here. Okay. So you have what's called a word. Okay. A word is this combination of the sign, the exponent, and the mantissa. Okay. So it's a signed exponent and the sign and the mantissa. In the computer, sometimes this sign is not stored, this exponent is stored slightly different from this, that we could have a finite number of bits for the exponent and 1 bit for the sign and a finite number for the bits for the mantissa. For example, you could have let us say 3 bits for the exponent, and then you would think that, okay, 1 bit is for the sign and 2 bits for the number. So instead of that, one could have all the 3 bits used for the number and have a convention that it always goes from minus that maximum number to the plus that maximum number. Okay, that's also possible. Okay, so that is, if you have 3 bits, then you have 2 to the power of 0, 2 to the power of 1, and 2 to the power of 2. Right, so that's 4 plus 2 plus 1, that's 7. Okay, so then you could say that it goes from minus 3 to plus 3. Okay. So that is one way of choosing this exponent. Right. So normally okay, for our convention, let's take this as a signed exponent, and this is a signed sign of the number, and that's a mantissa. And then we talked about normalization, that is the mantissa is such that the most significant bit is always 1. Okay. So that is what we saw, it is always 1, okay. It is normalized to 1, okay. So that bit need not be stored because it is actually 1 always. Okay. So that is the consequence of that is that the mantissa M is limited within this range, okay. That is, it has to be less than 1 of course, okay, and it has to be greater than or equal to the 1 over base, okay, because 2 to the power of minus 1, okay, is always 1, okay. That bit which represents 2 to the power of minus 1 is always 1, okay. So that means the mantissa is always larger than that, okay. The mantissa is always larger than 1 over b, right, but it has to be less than 1, okay, because whenever it reaches b, okay, whenever it reaches 1, that can be transferred to the exponent, right, okay. So for example in the base 10, okay, now you can have 0.5 into 10 to the power of 3, let us say as a number, 0.56 10 to the power of 3, and you keep increasing to 0.57, 0.58 and 0.9 and keep increasing this, and when it reaches 1, 0.99 and the next bit, then what it goes, it is to 0.1 into 10 to the power of, you increase the exponent by 1. Okay. So the mantissa is always limited between 1 by the base, okay, and 1. Okay, this if you have base 10, for example, the mantissa can't be less than 0.1 and it can't be greater than 1 because it goes into the exponent. And if it is base 2, the mantissa can't be less than 0.5, okay, because 2 to the power of minus 1 is 0.5, okay, or it can't be less than 1. Okay, that's the, so that's the, this is called a word, okay. So and we have the base, the mantissa and the exponent, signed exponent. Okay. We will see this the consequences of this again as we go along. So let us create a hypothetical floating point number set for a machine that stores 7-bit words. Let us assume that, okay, it is a 7-bit word. So now first bit, as we said, goes into the sign of the number. Now the next 3 bit, now let us assign the next 3 for the sign and the magnitude of the exponent. Okay, let us go for the convention just to understand the word. And then the next 3 goes to the magnitude of the mantissa. Okay, so remember we have 1 bit for the sign of the number, okay, 1 for the sign of the 3 for the exponent, of which 1 is the sign of the exponent, and 2 for the exponent itself, and then you have 3 bits for the mantissa. Okay, so that is represented here. Okay, so now we can ask the question that what is the smallest number which I can represent using such a word. So as we saw yesterday, that you cannot, there is a limit on the range of the floating point numbers. There is also a limit on the numbers, the number of the limit on the number which can go inside this range, right? That also we saw yesterday. So it's not a continuum. Right? So here let's look, now we are given this word. Okay, so we have 7 bits as we said. Okay, we have 7 bits. So 1 bit for the sign. Okay, this 3 bits is for the magnitude of, so 3 bit for the exponent, of which 1 is for the sign of the exponent and 2 for the magnitude of the exponent and 3 for the magnitude of the mantissa. Okay. So what's the smallest number which we can represent using this? Okay, smallest positive number, let's say. Okay, for example, let's take. So with this we say fixed to 0. Okay, that means its sign is positive. Okay. And if you want the smallest number, it's obvious that the sign of the exponent is negative. Okay, so we put sign of the exponent as 1. Okay, so 1 represents negative number. And then you have the magnitude of the exponent. Okay, the exponent has to be maximum, we know, maximum negative to get the smallest number. Right, so we put 1, 1 here. Okay, that means it is 2 to the power 0 to the power 1. And then you have the magnitude of the mantissa. Okay, so the mantissa is 2 to the power minus 1, and that's the smallest possible, right? Because it's normalized, so this has to be 1 always. So 2 to the power minus 1 and this 2 are put equal to 0. So that's the smallest possible. So then we could ask now the question, what is the smallest possible number? Okay, and then we would get it as the exponent would now, if you found that it is 2 to the power of 1, 2 to the power of 0, that is 3 with a negative sign. Okay, so the smallest, the number which you would get would be 0.5 into 2 to the power of minus 3, right. So that's the smallest possible. This is the smallest possible. Mantissa, we said base is 2, so the smallest possible mantissa is 1 over base, that's 0.5. And exponent we could maximum represent, maximum negative was minus 3, so we have 0.5 into 2 to the power of minus 3, so which is equal to 0.0625, right, in the base 10 system. So that's how we would write it, and in the base 10 system, now if normalized again, we would write it as 0.625 e minus 1, right, we saw that yesterday. Okay, so that's the representation of the number, and we can also get the highest number by similar way, right. So we can, then we would have all the mantissa, so we would have, if you want to take the highest number, we'll have all 1 1 1 here, and this will be 0, and this will be the highest number which is possible to get. So which can be obtained by increasing the mantissa by 1 by 1, right, and whenever maximum mantissa reaches 1, then we would transfer that to the exponent, okay, and again continue doing that, right. That's how we will go to the, that we represent all the numbers, and it's a good exercise to actually put in all these numbers and see what are the gaps, and you can also see that the gap increases, the gap between numbers increases as the number increases. We saw that yesterday on graphically. Okay, so what are the other points to remember on the floating point representation? That is, there is a limited range of quantities that can be represented, extremely important. Okay. Now, if you go anything more than that or anything less than that, you go less than the smallest number possible, smallest positive or smallest negative number, smallest positive number possible. If you go there you will get underflow. If you go larger than the number which is possible to store, you get an overflow. Right. And apart from that, even within this range, there is only a finite number of quantities that can be stored. So I am repeating this is extremely important. This is what we talk about loss of significant numbers. Okay, so there is a finite number of significant digits. So there is a finite number that can be represented within a range. Okay, that is, the degree of precision is limited, okay, because we have a finite number of bits. Right. So we have a finite number of significant digits. Okay, so there is, as I said, the precision is how close the two measurements are, but how close it can be is limited by how close the numbers can be represented. So there is a limited precision on a digital computer. Okay, this approximations. Now, apart from this, because of these limitations, when we represent numbers, we have approximations. We have to make approximations. We saw that, and for example, we saw when you try to represent pi, that we have to actually chop off at after some number of digits. So there are two ways of doing that, and we said either we can chop it off or we can round it off. Okay, they are called chopping and rounding. So chopping is merely to chop or cut off the higher digits. So that's what chopping is. In rounding, what we do is we would look at the value. For example, if it's a base 10 system, we would say that if it's more than 0.5, I will make it to the next integer. Right. So if it's 0.625, I will make it to 0.63. Or if it's 0.624, I will say it's 0.62. Okay. So then I would round it off. Okay. So that is that if there is some delta x which is fixed by the system which you use. Okay, and that allows us to represent it as we'll round it off to the next digit. Okay, so that for the earlier digit. So that's what we calling rounding. Okay, so rounding yields a lower error. Actually, rounding is plus minus 0. Okay, while chopping always gives you a plus error. For example, if it's 0.625, chopping is always 0.62. Okay, 0.626 is made to 0.62 if it's 2 digit. okay, while 0.62 will go to 0.63, 0.626 will go to 0.63 in the case of rounding. Okay, that's a difference. So there are two ways of representing an infinite series into a finite number on a computer. Okay, so we saw the interval between numbers increases as the number grows, and we said that is what is important for preserving the significant digit, and this also we saw yesterday. And then we said, okay, now with another consequence of all this, okay, that is a finite number of digits and a finite number of digits and a finite number of word length, okay, is that there is something called a machine epsilon, okay, because as we saw there is a smallest number. There is, given a word, there is a limit on the smallest number which can be represented. We just saw that on the 7-bit machine, it was 0.06, okay. And so that means there is something called a machine epsilon. So that is the number, okay, which if you add to some number, let's say 1 here, okay, I'm just taking 1 here, right, it produces a number which is different from 1. So you have you add some number to 1 and ask what's the result is, okay, and the result is more than 1. Okay, it looks trivial, but on a computer it is not, because there is a limit on the smallest number. Anything less than that is taken as 0, right? And since adding a 0 is not going to make a difference, there is a limit on that. Okay, so that is called machine epsilon. Okay, so that is given by b into 1 minus t. Okay, where t is the number of significant digits in the mantis. So b is the base. Okay, so once you got the machine epsilon, okay, if you know the machine epsilon, then you can fix the number of significant digits, because this is a relation. B is always 2 on a machine, right? So epsilon is b. Okay, it's not always 2, but if you fix b to be 2, okay, or if you know the b, then you can fix the number of significant digits. Okay. So remember, the machine epsilon is a number which has to be added, which when added to 1 gives you a number which is different from 1. So 1 I taken as something here, but you could add to a number, gives you a number which is different from that. Okay. So that's the machine epsilon. So which basically means that is the smallest number that the machine can store. That's fixed by b to the power of 1 minus t. Okay, so now having gone through the representation of numbers, and we know something about the range of integers, the range of floating points, and the precision and the number of significant digits, etc. Let's look at the consequences of that on arithmetic operations. So before that, we need to understand that how the arithmetic operations are done on the computer. We need to know that. So we look at some of the basic arithmetic operations. So, or like addition and subtraction. So how do we add two floating points? Okay. So to add or subtract two normalized floating point numbers, okay. So you remember the floating number is a point something something into base to the power of something, right? So that's base 10. You will have, as I said, 0.625 10 to the power of 2. Okay, and then you have to add this to something else. Okay, so when you add these two numbers, these normalized floating point numbers, which has a mantissa and an exponent, we have to make the exponents the same, right? We make the exponents the same, and then we add the mantissa. Okay. For example, let's look at how do we add in the base 10 0.4546 10 to the power of 5 to 0.5433 10 to the power of 7. So now how do we add this? So what we do is the one with the largest, this is a convention, okay, so not convention because it's normalized floating point. So we have to keep this, we have to make the exponent the same, remember. So how can you do that? If you have to do that, we keep this number with a larger exponent. We keep that this as it is, and we shift this and make the exponent 7. That means we would have to make it we have to add zeros here, we have to pad it with zeros. So it is 0, 0, 4, 5, 4, 6, 10 to the power of 7, and then we add the thing. So, but you see we have a fixed number of digits on the mantissa, okay, right. So you have to remember that. So then let's see what we get. Okay. So we shifted this. So the mantissa of the operand with the smaller exponent is shifted, right, to make the exponents the same. So we did that. Okay. Then we got 0.5433 10 to the power of 7 added to 0.0045. The rest of it is gone. Okay. So we don't have them anymore because we are only a finite number of digits, right. So we lost that numbers. Okay. Then we added to this. Okay. So now we see that because of the finiteness of the number of digits, okay, we have already lost something, right. We have introduced an error. Loss of some digits. Okay. So now this is the same way if you do the subtraction also. Okay. So when we have to equate the exponents, we have to make them the same. Okay. So the result of that would be that we would lose some significant digit. Okay. So remember, as I said, the number was actually 0.4546 10 to the power of 5, and we had to make it equal to the exponent equal to 7. So it was 0.0045, and we simply dropped this 46. Again, if it was we just chopped it. In this case, chopping and rounding will not make a difference because it's 4. If it was rounding, and if it's more than 4, then I would have made this into 6. Right? So that's what example of that is. Okay. So that's what we see, and then now we can go to the next operations, that's multiplication. So addition subtraction is the same. You add with minus sign, so that's subtraction, right? Okay. And now we can look at how do we multiply two numbers. Okay, so when we multiply this, we first multiply the mantissa and add the exponent, just like we multiply any numbers, and then we shift the mantissa such that it's normalized. Okay. So that's what's been shown here. Okay, so we multiplied these two numbers. Okay, so we got 0.227873, and we got exponent as we added the two exponents, and we got minus 3. Right? But the number of digits, we have written this here, the full number, but actually the number of digits is finite, we know. So we have only 4 digits here. Okay, so we're going to keep 4 digits. Okay, we're going to chop. We're going to just drop the rest of the digits. Okay. So any operations, as you can see, any operation which you do on any arithmetic operation, whether it is multiplication, whether it is addition, subtraction, division, almost always leads to loss of some digits. Okay. So this is something which we should always keep in mind when you write a program. We can quantify this, and that we will come to that a little later. So again, going to the division. Okay, in the division, again we would subtract the exponents, and we would divide the mantissa, and we would normalize it by shifting it again. Right? The mantissa of the number is divided by the mantissa of the denominator. The denominator exponent is subtracted from the numerator exponent, and the quotient mantissa is normalized to make the most significant digit non-zero. It's always carried out to make the most significant digit non-zero. Okay. And when you do this operation, you have to adjust the exponent. And here is an example again, particularly chosen to show that you would actually lose digits. Okay, so 0.1E5, 0.1 10 to the power of 5 is divided by 0.9999 10 to the power of 3. Okay, and we will get 0.1 10 to the power of 2. We know that this is, if you do this actually on a larger number, a larger precision machine, you will get a different value from this. Okay, but so that's what, if you have only 4 digits here, then you're going to lose some digits, and they're going to introduce some errors. Of course, nothing to worry. The error which we get on present day computers are much smaller than this. Okay, the minimum is 32 bits available today. So this is much smaller than that, but this is only to demonstrate that even though small, there is a loss of significant digit. Okay, so now what's the consequence of this? Okay, so we have always been taught in school that addition, subtraction, multiplication are associative. So what we see is that because of this loss of significant digit, we have slightly different rules for arithmetic on a digital machine. Example, arithmetic is non-associative. The reason being that we round it off or we chop it off and we lose some significant digits, and hence that introduces non-associativity of arithmetic. That is, a plus b minus c is not the same as a minus c plus b. Okay. A clever programmer will always keep this in mind when he is doing, or he or she is doing this calculations. Okay. So we have to make sure that the numbers we add or subtract are of the same order of magnitude, otherwise we would always get errors. So that's something which you have to always be very careful about. So a plus b minus c is not the same as a minus c plus b, and a into b minus c is not equal to ab minus ac. We will see this with some examples. So here is an example. Let's take a as 0.5665. If you have a calculator, you can try it out now. 0.5665. Your calculators always have more precision than this, so you have to actually approximate these numbers to get this demonstration working. So a equal 0.5665 10 to the power of 1, b is 0.5556 10 to the power of minus 1, and c is 0.5644 10 to the power of 1. So let's add a plus b first. Keep only 4 digits. You can round it off or chop it off. Do one of them always. So then we have, now we add these two, right? So we have exponents minus 1 here, plus 1 here. So we shift this to make this exponent same. So it becomes 0.0055 E1, that's 10 to the power of 1. And then we add these two matrices. So we get 0.5720 10 to the power of 1. Now we have a c, which is 0.5644 10 to the power of 1. So we subtract that from this sum. So that is 0.5722 10 to the power of 1 minus 0.5644 10 to the power of 1. Okay, sorry, there is some. Okay, this is actually 2. Sorry. So this is 0.5722 10 to the power of 1 minus 0.5644 10 to the power of 1. So we subtract this from this. Okay, then we get 0.7600 10 to the power of 1. And then now we do a different operation. Then we do a minus c first. Okay, and so when you do a minus c, you get 0.5665 10 to the power of 1 minus 0.5644 10 to the power of 1, and we subtract that first. Okay, so now we are going to do, instead of a plus b minus c, we are going to do a minus c first. Okay, and that leads to 0.21 10 to the power of minus 1, and then we add b to it, and we get 0.7656 10 to the power of minus 1. So there is a difference in the last two digits. Okay, so that's what I am trying to say. So we could say that that's the kind of error which we would have. We could compute the error actually, right, doing this two different operations and see what the error which you would get. Okay. And you know that if it's a full representation of the floating point, or if it's actually a real number, these are all treated as proper real numbers, then this error should not come. Okay. So we find the new rule that a plus b minus c is not equal to a minus c plus b, merely because of the finiteness of the word, that is that's a floating point representation. Okay, so now we saw that this disparity is due to the difference, the difference coming because of the finiteness of the number. Okay, so we should be careful when you do subtraction or addition or multiplication or division of numbers. Which are of completely different magnitude. So this has an interesting consequence that as I said that we have something called a machine epsilon, that is the smallest number which can be represented on the machine, okay, or the smallest number which when added to 1 would give you a number which is different from 1. Similarly, we also have a concept of 0. What is 0 on a digital machine? So when you are trying to do that, for example, let us take this quadratic equation, which is x squared plus 2x minus 2 equal to 0, and the answers are minus 1 plus minus root 3, right? We know that, we can solve this. So the question is, if I put this minus 1 plus minus root 3 back into this equation, what do I get? So if I get minus 1 plus root 3, okay, so what do I get? So minus 1 plus root 3 according to me is or according to the computer is 0.7320, right, and minus 1 minus root 3 is 0.2732 10 to the power of 1. My question is, suppose I put this back here, this number back into the equation, right? What will I get? Whatever I get is my 0. Okay. So that's something which we can look at. So now, okay, so we will see that we would see whether actually get that 0 or not. We'll just look at a program, okay, which would demonstrate this. So I have a small program here, okay, which would try to look at this. So I have represented these two solutions, okay. So one solution is minus 1 plus root 3, and I have taken the root 3 as 1.7320. I just took it like that, okay, because I think that's the only precision which my machine has. Okay. I am assuming that that's the only precision it has, my machine has, and I put that. And then I substitute that here and compute the value s. You know, if this is actual solution, I should get my s equal to 0, right? And then I take the other root, which is minus 1 minus root 3, which is 1.7320, okay, and then I compute the value s again, okay. So s1 here. So I call this root with minus 1 plus root 3 as x, and the corresponding value of the my quadratic equation as s, and the root with minus 1 minus root 3 as x1, and the corresponding value of the quadratic equation as s1, okay. And then I just try to now compute this value, and I print out both the 1 minus 1 plus root 3 and the quadratic equation, the value of the equation and the value of the expression, and the second root, which is minus 1 minus root 3 and the value of the expression, and then we will just see what we get. Okay, so that's what we get. Okay, so we don't, what we are supposed to get is 0, because we said that it is a 0 of the it's a 0 of this, it's actually the solution of this equation, or the 0 of this function, right. It's a solution of this equation which we wrote as minus 1 plus or minus root 3, which we know, right. So now I am approximating root 3 as 0.1732 10 to the power of 1. That's what I would have with 4 digits for the mantissa, correct. So now I put that back here, okay, and I am looking at what is the value I get, and I see I don't get 0. Okay. So if I have 4 values, or if I have 4 digits for the number, 4 digits for the mantissa, okay, and then I am going to get the 0 as 0.001, right. I will, for 4 digits, if I just get 0.001, or if I chop it, okay, or 0.002 in the case of rounding, that is what I got the value as. So that introduces this idea of 0, okay, on a machine. So you have to be very careful when you are actually programming, that you should not be saying equation, you should not be equating or a number to 0 as a condition, okay. For example, if you want to put an if statement and if you say the solution of this equation, if the value of some expression x minus something, x minus 3 is equal to 0, x minus 3.0 equal to 0 as a condition, and we assume that when x is a solution of x, for example, x was a solution of this equation, okay, and we said that x plus or x minus 1 minus or 1 plus root 3 is equal to 0 as a condition of something, and then you will get into trouble. So because the 0 on the computer is not the word 0 you think it is. It is always actually a finite number. Okay, that's what should be careful about. So always avoid equating to a 0. So we have to say that instead of saying a minus b equal to 0, we have to say a minus b less than some epsilon. That epsilon is the smallest number which the machine can represent. So that's what you have to be careful about. Otherwise, you will never get the condition correct. Okay, so that's care should be taken when you compare two floating point numbers in the condition for computing. So now we saw that there are many errors. Right? So we have errors coming because of the finiteness, because of rounding, chopping, and because there is only a finite number of floating points I can store given the range, etc. So now how do we quantify this? Okay, so we need some way of quantifying these errors. Okay, so that's what we would discuss next. So the errors can be classified into two. We can have errors due to truncation. As we said, we have 1 by 3, okay, or some large number, there's a series like that, and then you need to chop it off somewhere, okay, or root of pi, for example, we need to chop off somewhere. We have to truncate this number. Okay, that's some truncation errors which comes from that. And then we also have errors coming from, for example, we saw when you add, subtract, multiply, we have some round off errors coming from that. So there we have these two errors. Okay. So now the question is, how do we compute the errors which are, and then make sure that our calculations are within the error limit, or at least we should be able to say, okay, I have done this calculation and my error, possible error in this is so, an upper limit on that. Okay. How do I say that? What is the quantities, right? So that's what you should try to see. Okay, so if you know the exact value, okay, then we know that the true value is approximation plus the error, okay, and then this relationship we can use to actually quantify the error. Okay. But the problem with this is it doesn't represent, it doesn't give us a feeling for the magnitude of the quantity which you are measuring. For example, you could measure a distance of 1 kilometer or 1 meter, okay, and make an error of a centimeter. Okay. So according to our previous definition, that is the true value is the approximate value plus error, or if you take the true value minus approximate value as the error, okay, both will have the same amount of error. Okay, but that doesn't give us a feeling for that. Okay. So we need to have a fractional error. Okay. That is, for example, if you measure a rivet or a bridge, okay, and if you make an error of 1 centimeter, okay, that doesn't have the same significance, right? So we need something which represents or which reflects that significance of the error, and that's why we say we use a fractional relative error. That's error divided by the true value. Okay. So this can be, we will always express this in terms of percentage. You say error by the true value multiplied by 100. Right? So that's a percentage error. So now the question is, most of the, okay, now let's look at some example of this. So that is 9,999 centimeters, where the true value was 10,000 centimeters. Right? Or then we have 9 centimeters where the true value was 10 centimeters. Because the measuring instrument you are using was at an error of 1 centimeter. So now, so what does it mean? So the error in the first case would be 1 centimeter, the error in the second case would be 1 centimeter again. Okay, that doesn't signify much. Okay, so what we have to do is we have to have the percentage error. The percentage error In the first case, it would be 1 by 10,000 multiplied by 100. That will be 0.01%, while the other case it will be 1 by 10 multiplied by 100, that is 10%. Right. So that gives us much more feeling. Okay. We have 10% error if you use a scale with 1 centimeter as the 1 centimeter precision, and if you measure something of the order of something like a rivet or something, a 10 centimeter object, we have 10% error, and while if you measure the bridge with it, we have an error of only 0.01%. That is what it means. So both the errors are 1, but the significance is different, right? So that is what we said. Another case of importance is where we do not know the true value, and we still wanted to say what the error is. So the question is, how do we quantify that? Suppose you do not know the true value and you still want to quantify it. Okay, so how do we do this? Okay. So in that case, we can actually use two measurements and take the relative error between that, right? So that is, we have an approximate error. Okay. So that is, we will do that with again with an example here. Okay. So we have an approximate error divided by the approximation into 100. Okay. So that's the kind of a percentage error again, okay, but not with a true value. Okay. So normally it's represented with a subscript a. Right. So there's a definition that you would see everywhere when you look at error analysis for a numerical computing. I think that you would see this kind of numbers represented. So epsilon is the true error, and epsilon a is the approximate error. Okay, which is probably the difference between two measurements divided by the mean of that measurement multiplied by 100. Okay, so for example, in iterative procedures, this is very meaningful, right? So you could take, let's say, if you want to measure, if you want to compute e to the power of minus 0.2 or something like that, okay, and then you say that, okay, I would represent this as a series, okay, and then I chop off the series somewhere. Okay, the question is how many terms in the series should I keep? So then, for that kind of measurements, okay, it makes sense to actually have a definition of the error in this form. Okay. So as I said, you could take, for example, 2 by 3. Okay. So 2 by 3, you start doing that. Okay. Then you get 0.6666. Okay. And then you want to know where you should stop, how many digits you should stop, and then you say that, okay, I could use a kind of error definition, and I say my my error in this calculation is this much. Okay, I don't care if it goes if the percentage error is something of the order of 10 to the power of minus 3, okay. And then I could keep different each term in the series, okay, each term in that number of digits, okay, and then I could compute the difference between 0.66 and 0.666. Okay, and then divided by the present approximation, which is 0.666, and then see what the error is. The sign is not important here, so what's only important is the magnitude. Okay. So that's the kind of that's an example which I said. So for example, another example would be computing the exponential series or the log 1 plus x series, similar things. Okay. So we will see that in an example when we actually quantify this in some programs. The sign is, as I said, the sign is not very important. What's important is only the magnitude. Okay. And so what we do is we would compute this kind of an approximation, the present approximation minus previous approximation, and then divided by the present approximation, compute the percentage error, and then we compare it with some predetermined error. That's like, as I said, 10 to the power of minus 3 is my predetermined error, which is or my tolerance. So that's fixed, and then I compare it with that. If it is below the tolerance, I say this is acceptable. This number is acceptable, and that series can be terminated there. So that's what the computation is generally repeated till we go below this limit. So now there is an important thing to remember that the details of which I will not go into. Is that it can be shown that if a criterion of this order is met, that is, if you say that epsilon, okay, if I put a machine, if I have machine, if I want a precision, okay, up to certain number of digits, okay, that is n is my number of significant figures, then on a machine with base 2, then 0.5 into 10 to the power of 2 minus 1 percentage, okay, would tell me that my answer is as the number of significant digits as n. That is, if I fix my epsilon s as 0.5 into 10 to the power of 2 minus n, okay, and then if I do a computation and make sure that my approximate errors are less than that epsilon s, then I will have n significant digits in my answer. Okay, so that's the point. So if I want to keep n significant digits, I should have, on the other hand, if I want to keep n significant digits, then I should keep my tolerance as 0.5 10 to the power of 2 minus n percentage. Or in other words, if you have a machine with n significant digits, okay, there is no point in keeping a tolerance which is less than this. Okay, that's the maximum tolerance which you get. That's the minimum which you can get, okay, in your error. If you go to the next term in the series, you are not going to get a better answer, okay, because it's not meaningful to go beyond this. So remember that 0.5 into 10 to the power of 2 minus n percentage. Okay, that's if you have three significant digits, okay, and then three significant figures. If you want to compute e to the power of 0.5, let's say, and then the correct we can expand this in a series, okay, and make sure that the difference between two approximations in the series divided by the present approximation is 0.05 percentage, is below, it's of the order 0.05 percentage. Okay, you should not try to go below this, it doesn't make sense. So that's what we would see the series. For example, if you have e to the power of x, I can write it as 1 plus x squared by 2 factorial x to the power 3 factorial, etc. We know that. Okay, and then we should keep different terms. So first term is just 1, and we just saw that if I do x to the power of 0.5, okay, the correct answer is 1 point something, 1.6. What I forgot. So we have 1.64872, let's say, okay, as the correct thing. So if you do just the first term, then we get 1, right? So and if you keep the second term, then we're getting 1.5. So then we take 1.64 minus 1.5 divided by 1.5. That's one possibility. That's a true error. Okay. Or you could say that my relative error here is 1 minus 1.5 or 1.5 minus 1, since we are not bothered about sign. 1.5 minus 1 divided by 1.5 into 100. So that should be less than 0.05. That's what we want to do. Okay. So here the first term, the true error is 1.648 minus 1.5 divided by 1.648 into 100. That's 9%. Okay. While my approximate error was 1.5 minus 1 by 1.5, and that is 33%. Okay. So we go to the next term in the series, etc., till this error goes to 0.05%. That's what we saw is the error which we can tolerate. Okay, so we go to the next term and continue this series. So we can summarize this computation by taking various terms in the series, and we will keep going down on the percentage error and the true error. Okay. So the approximate error and the true error, and we can actually see the true error converges much faster than the approximate error. Okay. In this case. Okay, so now we should look at some problems which is listed here. So you can just try to find the error in the value of x cube at x given 4.0 by 3.0, and then you could approximated with different representations. This floating point here 4 by 3, right? So it's 4.0 by 3.0. You could approximate it with different floating point representations and compute the errors. Okay, that's one example which you should try. Okay. That's, for example, you could try it with base 10 and keep the 4 significant figures on the mantissa and take an exponent which goes from -2 to +3. Okay. Or you do with base 2 and keep 4 significant digits and then go from -2 to +3. Okay. With the exponent -2 to +3 and compute what the error is. So we would now have to look at how does this error would propagate. Okay, as it means we saw that every arithmetic operation would introduce some error. Okay, and we know how to compute this error. Okay, another important thing to actually figure out how do this error would propagate. Okay, in a computation, and that's something which you would see later. So in summary, we saw there are 2 types of errors encountered in the numerical computation. We have round off errors due to finite representation of numbers. That is, we said, for example, 1 by 6 cannot be represented completely, so we have to completely represent it as some approximation to this, right, because there's a finite number of digits. Okay. And then we have rounding errors which appear due to arithmetic operations using finite digits, which also we saw in using few examples. Okay. So then we have truncation errors. For example, if you have a series, then we would truncate that. Okay, so we have finite representation of numbers, and then we have when you do arithmetic addition, subtraction, we have round off errors, and then we do a series expansion. For example, we have truncation errors. Okay, all coming from the finiteness of the number. Okay. For example, if you instead of using in a full expansion for a sin x or cos x or a log x, we could use some kind of a series, and then we truncate that. That is gives you some kind of truncation error. Okay, so we would look at examples of this and actually how they would come in the next class. Okay, so the total numerical error in that way. So now we can summarize it here. The total numerical error, okay, is the summation of the truncation and round off errors. Okay. So that if you want to minimize this round off errors, we know round off errors come because this number of significant digits are finite. Okay, so the only way we can actually minimize the round off errors is to increase the significant figures in the computer. Okay, but the round off errors will increase due to subtractive cancellation or due to an increase in the number of computations. Okay, that is also true. Okay. So now if you try to, for example, in a series, we try to, if you in computation, we try to increase the number of steps in something. Okay, and then you would have subtractive cancellations coming in. Okay, which would also increase the errors. Okay. So this part of there's actually a trade-off. Okay, in increasing the round off errors and also the truncation errors. So that's something which we should look at in detail, and that is something which we will do in the next class. So I will stop it here, and we'll continue from this propagation of errors, or actually quantifying the number of the different types of numerical errors which is coming in, and where is the what is the optimum way of what is the optimum in the method, what is the optimum method to compute various quantities. That's what we should be looking at in the next class.